Hey guys, Miss Marisic here, and in this video we're going to talk about strong acids and bases versus weak acids and bases. Now, quite a bit of what you're going to hear in this video is a review, so you're going to hear some things that should sound familiar, but you also might hear quite a few new things as well. With that said, remember that the big key difference between strong and weak acids and bases is how much they dissociate. How much do they split up into ions? And so you see here two particle diagrams, one representing a strong acid and one representing a weak acid. And the way I would pick these out is by looking how many of our particles have dissociated or split up into ions. In this diagram here, we notice quite a few molecules still together and only a couple that have dissociated or split up into individual particles, into those individual ions. So therefore, I can conclude that this would be representative of the weak acid. It is only partially dissociated into ions. However, on this particle diagram here, I notice that all of the molecules have split up. They're all separated into ions. And so therefore, I can conclude that this would have been representative of the strong acid. Weak bases and strong bases would look very, very similar. You would notice for a weak base that you would still see particles together, whereas for a strong base, everything would have split up into ions. Now, we have below kind of a table that compares our weak and strong categories. So let's go through these different traits. The first thing it asks is to what percent do they dissociate? To what percent do they split up into ions? And for a weak acid and base, that percentage is going to be below 100. And I'll be honest, often it's below 5%. It's very little of it that actually splits up into ions. And so we are going to have to use equilibrium constants to do these calculations. And actually, one of the calculations that we'll perform is actually figuring out that exact percentage to which it dissociates. However, for a strong acid and base, it 100% dissociates. Everything's going to split up into ions. Now, both weak and strong acids and bases conduct electricity. We do make at least some ions. However, for weak acids and bases, that conductivity is going to be pretty poor. There's not a lot of ions there to help pass that electrical current along. However, for a strong acid or base, because everything's making ions, we can pass that electrical current very easily. And so that would be a strong conductor of electricity. Now, we haven't talked a whole lot about pH scale yet. That's going to be in one of our upcoming videos, but I know a lot of you have some background with it. The pH scale, which goes from 0 to 14, is a scale that basically ranks acids and bases. Something that is acidic is considered below 7 on the scale. Something that is basic is above 7 on the scale. 7 is our break point of being neutral. So what we'll notice is that with weak acids and bases, their pH values tend to be closer to 7. You know, like maybe a weak acid might be somewhere in the 5 to 6 range, whereas a strong base might be in like 8 or 9. However, once I get to the strong acids and bases, because they're making so many more, in the case of acids, hydrogen ions, or in terms of bases, hydroxide ions, those pH values get to the extreme ends of this scale. You end up much farther from 7 with those strong acids and bases. Something we've talked about quite a bit in the past is with a weak acid or base, we do put that two-way arrow, meaning we make equilibrium. Whereas with a strong acid and base, we would put a one-way arrow anytime we show their dissociation equation. Now, this next two questions kind of work in tandem with each other. It says, would equilibrium lie more to the reactant or product side? Basically, do I have more reactants or more products at equilibrium when they're dissociating? And also, is the value of the Ka or Kb large or small? Well, remember, for a weak acid, if it's dissociating, very little of it is making product. So most of it would stay on the reactant side. And that would indicate a very small value for a Ka or Kb. Remember, that's just the equilibrium constant itself. However, for a strong acid and base, it's going to basically completely go to product. Those Ka and Kb values are so large that that we essentially say it goes to completion, and so we would use stoichiometry to do their calculations, whereas with the weak acids and bases, I would have to use equilibrium. Now, it wanted us on this next part to compare for a monoprotic acid the hydrogen ion concentration with the original acid. You could also do this for bases. You would just compare the base to the OH concentration. And what you'll notice is that for a weak acid, the acid concentration to start off with is going to be much higher than the resulting H plus concentration after it dissociates. Because remember, I'm still going to have quite a bit of that acid left at the end after the dissociation. I'm only going to make a little bit of those products. But notice that over here on the strong ones, that acid concentration to start off with ends up equal to the hydrogen ion concentration at the end, as long as I'm only making one hydrogen ion. That's why it's specified over here, monoprotic. And so you notice here what happens is the HA, that original acid, completely goes away. I don't have any of it left here at the end. All of it has become the hydrogen ion along with the anion. And so that hydrogen ion concentrations ends up in the same mole to mole ratio as the original acid concentration to start off with. Now, as some reminders of something we were supposed to memorize, but I know not everybody has yet, we want to make sure that at some point we memorize what are considered strong acids and strong bases. If it's not on this list, then we assume it to be weak. And the strong acids that you want to be familiar with are hydroiodic, hydrobromic, hydrochloric, nitric, sulfuric, chloric, and perchloric. Now, a couple quick notes. First off, on sulfuric, technically only the first hydrogen coming off is strong. Once I get to HSO4 -1, the second hydrogen coming off is actually weak and would end up forming an equilibrium. Also, some textbooks include chloric and some do not. AP will probably not ask you about chloric for that very reason, but just keep in mind that when you take chemistry in college, you may see chloric included and you may not. It's kind of one of those that's on the border between being strong and weak. For strong bases, these are our group 1 and 2 hydroxides except Be and Mg. So think like sodium hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide, all those group 1 and 2 hydroxides. So if it's a hydroxide that's not group 1 or 2, like for example, aluminum hydroxide, that would be a weak base. If it's an amine base, one of those nitrogen bases like ammonia, it would also be weak. So again, anything not on those strong lists would be considered to be weak. And so therefore I would need two-way arrows being used instead of one-way arrows. So you want to make sure you are familiar with that list because it's going to really impact how we would solve a problem. All of these strong acids and bases, I can use stoichiometry to solve their concentrations. They're really easy to calculate. But if it's not on this list, then that means it's weak and I would have to use equilibrium calculations to figure out my ions. So it makes our problem completely different depending on if we have something that's strong versus weak. Now, one last thing that's affected by something being strong or weak is the way I would use it in a net ionic equation. And so what you're going to see on this next page is actually a little bit of review from when we did net ionic equations. Okay. So let's start off with recapping an acid-base reaction. That is where we have protons that have been transferred from one species to another, where we saw our conjugate pairs, something acting as an acid, something else acting as a base, one thing giving off a proton, something else accepting it. But there's a special subcategory of acid-base reactions where we have an acid and a typical hydroxide-containing base. And if we have that situation, then what happens is that water will be produced in the process. And if water is made, then we will often call it a neutralization reaction, because in a neutralization, we make neutral pH-wise water. Water has a pH of exactly 7 on the nose. However, we have to be really careful with our acids and bases and whether or not they are strong or weak. And the reason why is because if I'm trying to write a net ionic equation, strong acids and bases get dissociated, but weak acids and bases get left together. And so we have to make sure we're identifying what kind of substance we have when we're trying to construct those net ionic equations. So we're going to look at two examples here. The first one wants us to write and illustrate the net ionic equation between nitric acid and calcium hydroxide. So the first thing I would do is take the time to figure out, is it on the strong list or not? Nitric acid, HNO3, is on that strong list. Calcium hydroxide is a group 1 or 2 hydroxide, except Be and Mg, and so it too is strong. And so when I put those together, I would do a double replacement reaction. So the hydrogen and the hydroxide would pair up to make water. The calcium and the nitrate would pair up to make calcium nitrate. Notice I make sure to balance out all my charges. I then went and put states with everything. The product over here of calcium nitrate would be aqueous because it had the nitrate in it. And as we remember, all nitrate substances are soluble. However, the H2O, the water, would be a pure liquid. So all I did first was write my overall balanced reaction. But eventually I want to get to the net ionic. So what I did next is I constructed a complete ionic equation. I took everything that was AQ and split it up into ions, as long as it was strong or ionic. Remember, if it's a weak acid or base, even though it's AQ, it would stay together. However, here, since we said both things were strong, I didn't have that problem. So everything that was AQ got split up into their ions. However, I did leave the water together because remember, I always leave together pure liquids or solids, okay? Our last compound here was aqueous as well, so that got split up. So then what I would do is, before I get to my net ionic, I need to pick out my spectator ions. I need to pick out anything that stayed the same from side to side. I noticed I had nitrate ions and calcium ions that stayed exactly the same from side to side. So those were the spectators. And so my net ionic equation would be written without those spectator ions. So I'd have the hydrogen ions plus the hydroxide ions forming our liquid water. Notice I did go ahead and reduce it down. Originally, it did have 2 in front of everything. So instead of putting 2, 2, and 2 for my coefficients, I reduced those down to 1, 1, and 1. So then when I came down here to my particle diagram, I showed my nitric all split up, my calcium hydroxide all split up to start off with, and then we ended up forming water with the 2 nitrates and the calcium ion remaining as our spectator ions there. So now let's look at another example. On this one, I have nitrous acid and lithium hydroxide. Now, nitrous acid, remember, OUS endings have ITE polyions, so this would have had nitrite in it. However, HNO2 is not on that strong list, and so therefore it would have been considered a weak acid. Okay, now the lithium hydroxide is a strong base because it's a group 1 or 2 hydroxide. However, that doesn't change what I do over here on this complete reaction. I still am going to do a double replacement. Where it plays a role is when I start to think about splitting up my ions. Okay, so that's where we got to pay careful attention if it's strong or weak. So again, all I did here was a double replacement. H and OH made the water. Li and NO2 made LiNO2. It was aqueous because it had something that was in group 1, and all group 1 salts are soluble. So now, when I get to my complete ionic, this HNO2, even though it has aqueous in front of it, needs to be left together. Why? Because it's a weak acid. Weak acids and weak bases, even though they have AQ, need to be left together. And the reason for that is I'm trying to represent what the bulk of that solution is doing. And remember, we said that weak acids and bases dissociate less than 5%. Well, I'm not going to address what 5% of the solution is doing. I want to address what the 95% of the solution is doing. And the 95% of that solution is staying together, which is why I leave it together here. Now, lithium hydroxide was a strong base, So that would get split apart because, again, 100% of it is going to dissociate into ions. Water gets left together because it's a pure liquid. Our LiNO2, our salt that we made, is going to dissolve into ions because it was a soluble ionic compound. So now notice that the only spectator ion here was the lithium ion. That was the only thing that stayed together from side to side. And so our net ionic equation here looks very different than the one we saw up above. This time I have that acid written all together in there, HNO2, with the hydroxide ion forming my water and my nitrite polyatomic ion. The only spectator here was the lithium. So on my particle diagram, I would leave the HNO2 together here. Now you notice I put a comment down here. I put that there's very few ions of H and NO2. The reason why I put that is because technically, are there a few of those ions in there? Sure. Remember, it dissociates just a little itty bitty bit. So to really show on a particle diagram that little itty bitty bit, I would have to draw, 100 of those HNO2s and maybe one hydrogen ion and one nitrite ion. And that's just a little unreasonable to expect out of a particle diagram. So just keep in mind that these particle diagrams do have their limitations. You can't do a perfect particle diagram here because you're not going to get that perfect ratio and you're not going to be able to show that equilibrium that would be existing in that container. However, our other container here, all of our lithium hydroxide would have split up into Li and OH ions. And so then when I come over here, I would have my water that I produced, my lithium ions that are spectators, and then my nitrite ions that are still in that solution. So hopefully this kind of looks familiar. We did do some of this back when we did reactions in Unit 4. So if it looks familiar, that's probably why. If you have any questions or need any help, please feel free to email me. Bye, guys.